Okay, good afternoon. This is the next lecture in 569 Emergent States of Matter, February the 22nd. So what we did last time was we spent a long time talking about the phenomenology of superfluidity, and in particular we understood how the idea that drag can be reduced, or in fact basically set to zero, if the superfluid is made up of two components, a normal component and a superfluid component. And the superfluid component is a irrotational field, meaning its curl is zero, whereas the normal fluid component follows the usual behavior of Navier-Stokes equations. And we went and talked about how heat is transported, and we talked about the fluid mechanics of that. And at the end of the lecture, we talked about the thermomechanical effect, how entropy is transported, and the interplay between the fountain effect and the conduction of heat due to the thermal excitations in the fluid. So what the last thing that we talked about was counterflow, and now what I want to do today is I want to carry on where I left off, but talking primarily about the way in which superfluidity is a consequence of some form of Bose-Einstein condensation. So our goal today is to talk about superfluidity as an outcome of a generalization of a Bose-Einstein condensation. And the important point about the generalization is that we're going to be talking about systems that have strong interactions. And what we're going to see is that we can devise a measure of a quantum order and what we will do is we're going to apply that to the case of ideal bosons. And then what we're going to be doing is we're going to examine the consequences of this quantum order for interacting systems. And perhaps the most interesting thing that we're going to see from this is the idea that you have a wave function, a macroscopic wave function that describes 10 to the 23 particles, and as a result of that, one has topological defects. And so what we're going to get into is the precise behavior of quantum vortices. Okay, so let me keep this page up here, and let's go over here. So this is section 2.4 in my notes. So the basic idea in this section is that the two-fluid model is naturally interpretable in terms of Bose-Einstein condensation. So what is the obvious interpretation? So the idea is that the condensate is something like the superfluid component. And the excitations above the condensate are the normal fluid component. So the so that's the basic idea, and the caveat that I want to make about this is that what we're going to see is later we will see that an ideal Bose-Einstein condensate is actually not a superfluid. And the reason I say that is that it has a critical velocity of 0. So remember what the critical velocity is. So the idea of the critical velocity is that you get dissipation as flow only for velocities or speeds smaller than some critical amount. And you know why that is and so on is we will talk a little bit about that. And so this is a limitation of superfluidity. You have to be below a critical velocity. And what we're going to see is that for an ideal superfluid, for an ideal gas of bosons, they will form a quantum state of order, but it is very easily destroyed. And so what we will do later is we will put in interactions and use a second quantization to calculate what really happens when you have interactions. So what that's going to mean then is that later we will add interactions to our ideal bosons and see how a weakly interacting Bose gas is superfluid. So that's the first thing. Now there's another thing that I want to point out or remind you of about ideal bosons. So a second point is another similarity between BEC and superfluidity, and that is heat transport. So you'll probably remember this, but if not, look back in my notes. That if I have a Bose-Einstein condensate, then the pressure in that Bose-Einstein condensate, the pressure only depends on temperature. And not the density. Okay, so that's not something that would be true in a regular gas, but it is true in a Bose-Einstein condensate. And so what does that mean? So the implication of this is that a temperature gradient will cause a pressure gradient. Now, how do pressure gradients relax? So pressure gradients in a gas usually relax by sound wave. And that's the usual thing that happens. You have a wave of pressure and density that propagates throughout the gas, and that's how you can hear what I'm talking about right now. So then you might expect that if I make a temperature gradient, so that this would suggest that if I make a temperature gradient, it will relax by propagation at the speed of sound. And not purely diffusively, as you might naively expect. Okay, so that's a pretty strange expectation, but actually it turns out to be correct. So this is actually basically correct. So I'll say it's directionally correct, and the propagating mode is called second sound. So real sound is a density wave, and this sound wave is not a density wave. It's a temperature wave, and because it's a temperature wave, it is a entropy wave. So it doesn't involve changes in density, but it does involve changes in temperature and entropy. And so what we can say is that this mode involves changes in temperature and therefore entropy, and not density. So it's distinct from first sound. So what we do is we reserve the name first sound is the excitation which involves density variations. So I've now told you that there's at least two sound modes in the superfluid helium. Now, how can you have a mode which is propagating and involves temperature but doesn't change the density? Well, remember what we talked about at the end of last lecture. We talked about this idea of counterflow. So counterflow is a flow where there is no net mass transport. And so the other thing that we may anticipate is that the second sound mode will be a counterflow. And that way you can preserve the constant density. So even the normal and superfluid densities may be locally varying, the overall density doesn't change. and that is the idea that we're going to be using here. Okay, so that's that's what we're going to see happening. So now let's talk about the question of, does Bose-Einstein condensation occur in helium-2? I'm not going to go into this in great detail. So that's the question, and the answer is yes, it does, and we know this for two reasons. The first way we know this is we know that neutron scattering experiments well, actually, I'm going to talk about computer simulations first. So computer simulations and neutron scattering. Tell you why. So let me just talk about computer simulation. So what you do in computer simulation is you model the helium as hard spheres plus some attractive Leonard-Jones potential. And then what you do is you solve the Schrödinger equation using an exact method, as exact as you can get, known as quantum Monte Carlo, which I'm not going to go into. But if you want to know about that, I'm sure David Sepperly has courses where he discusses all those things, and then what you try to find is what you measure is the fraction of particles in the zero momentum state. And if you remember, Bose-Einstein condensation is a non-zero fraction of particles in the zero momentum state, and what you find is that for zero pressure, something like 10% of the particles are in the condensate. So why only 10%? So if we were looking at a ideal bosons at zero temperature, what you would expect is that 100% of the particles are in the condensate, the zero momentum state. And so what happens is interactions between the particles cause them to occupy excited states in the real helium-2. So the effect of the interactions is to deplete the condensate. And later we'll calculate that effect precisely. So we'll actually calculate that explicitly using a second quantization. So that's what we do with computing. Yep.
Can I ask a question? When you're simulating the helium-2, does each sphere have its own kind of like attractor on it, or is like kind of like a background potential and all the spheres are interacting?
No. All the spheres are interacting through a pair potential, and the pair potential is a hardcore repulsion and then a long range attraction. We're going as 1/r to the 6.
Okay.
Okay, so if you remember the Lennard-Jones potential, typically Lennard-Jones is called 612. It has a repulsive part that rises as 1/r to the 12th, and then it has an attractive part that rises as 1/r to the 6, which is due to dipole-dipole interactions. And so the model of it that people can use is it's easier. Why use a 1/r to the 12 when you can just simply use a hardcore repulsion?
Right.
Okay. So then the other modality that we can use is experiment, of course. So the experiment that you do is you scatter neutrons. So let me just say a little bit about that. So if you take the idea is to use a high energy neutron. And what that can do is that can transfer energy to a single particle, a single atom, and then it will propagate until it is scattered. And so the idea is the following. You have your target like that. So here is your helium-2, and then incoming you have some neutron coming in like this. So here's your neutron with some wave vector k, and then it gets scattered at some angle like this, and comes out with a wave vector k prime. The momentum transferred is k minus k prime. This is meant to be kappa, pretty bad choice of notation, and so this thing here is momentum transfer. And of course there's also energy transfer as well. So there's a change in energy in elastic part h bar omega. And so what do you measure? So I'm not going to go through this in great detail. So what you measure is essentially the Fourier transform of the 2-point correlation function in space and time. And so when that means that what you essentially measure is an object which will write as S of k and omega, and this is the so this is, if you like, you can think of this as being the density as a function of k and omega squared, something like that, thermal average. So if you don't know about correlation functions, don't worry about it. Some of you I know are doing it for your research work and so on. So basically this is just a measure of 2-point correlations in space and time, Fourier transformed, and so you get into k space and omega space. And the most important thing is that if you have a condensate, so if you have a condensate at 0 momentum, then what you find is that S of k and omega, actually kappa, S of kappa and omega is going to be some number, which is the condensate fraction, plus some function here. So this basically says that the energy is given by h bar squared k squared over 2m. This is the number of particles in the ground state. And so those particles move according to how far they're kicked, because they don't have any other momentum. And this part here is some broad background from excited state particles. So what you can see is that from this kind of measurement, you can then measure the presence of the condensate. So this is a very basic idea of what happens. So that's fine. That's what you measure. That's why we believe there is quantum order in a superfluid. So how do we calculate that? So this is section 2.4.2. This is off diagonal long range order. We'll call this ODLRO. So this is very important, this section, because this is really the where we're going to start using a second quantization. So we're going to just jump straight into this. There's going to be a little bit of formalism here. So feel free to ask me any questions about it, but I think you should be well set to do that. So the goal of this section is to devise a measure of a quantum order that is a generalization of just looking at the condensate wave function, Bose-Einstein condensation. So what is off-diagonal long-range order? So it's a property of the single particle density matrix. So it's not a correlation function. So let me explain what that is. Even if you don't know what a single particle density matrix is, you in a few minutes you'll see what it is. So let me define it, and then I'll unpack the definition for you. So what we're going to define, so what this single particle density matrix is this thing. So we're going to call it rho of R and R prime. So that's the single particle density matrix, and we're going to define it as a thermal average of psi dagger of R, psi of R prime, like so. And now I'm going to tell you what all these different terms mean. Okay, so bear with me. So first of all, what do the angle brackets mean? So these angle brackets, these mean a thermal average in quantum statistical mechanics. And so how do we define that? Well, we just take whatever is inside here, let's call it some operator O, and then what we do is we compute the matrix elements of this operator, whatever it is, between energy eigenstates. We weight those eigenstates by a Boltzmann factor, e to the minus beta n. We sum over eigenstates, and then we normalize by the partition function. So that's what we mean by a thermal average, and beta is, of course, 1 over kT. And so here, Z is the partition function. So that's just simply the sum over eigenstates e to the minus beta En, and the eigenstates themselves are eigenstates of the Hamiltonian operator. So I can write those as satisfying the time-independent Schrödinger equation like so. Okay, so
Question.
Yep.
Are we using canonical ensemble or grand canonical ensemble here, or is that important?
For now, just think that I'm using canonical ensemble.
Okay, thank you.
But later, but the obviously we can generalize this to grand canonical ensemble just by replacing the En by En minus the chemical potential. So for now, just think of it like canonical ensemble. Okay. So now let's talk about psi. So psi of R. So psi is called a field operator. And the way to think of that is just it's essentially a Fourier transform of the annihilation creation operators. So what we think of then is an annihilation creation operator AK, which will create a particle in a plane wave state with momentum K. And so the field operator is just the Fourier transform of that. So let's write it down exactly. So I'm going to define psi of R is 1 over the square root of the volume of the system, the sum over K e to the I K dot R times the operator AK, and psi dagger of R is 1 over the square root of V, sum over K e to the minus I K dot R AK dagger. So these are annihilation and creation operators, and they satisfy the following relations. So I'm going to write them down like this. I'll give them the subscript I to represent a state. So I'm going to write down the occupancies of the states N1, N2, N3, up to Ni. So this is just the square root of Ni times N1, N2, Ni minus 1, and so on. So that removes a particle from the state I, and similarly AI dagger acting on the same thing gives you a factor 1 over 1 plus Ni acting on N1, N2, and then Ni plus 1. So that's what annihilation creation operators do. And when I write down these cats, so this state this is a many particle quantum state. with Ni being the occupation number of the ith single particle quantum state. So we've chosen some basis. We've written down our many-body state like this. If we're in a system which is translationally invariant, then we know that these states are going to be the eigenstates, so translate of momentum. So translational invariance means that we use the momentum eigenstates. And then once you have this, then you can write down the commutation relations. And so you already know this, so I'm not going to waste time deriving them. So AI AJ is equal to AI dagger, AJ dagger, and that is equal to 0. And similarly, AI AJ dagger is just delta IJ. So that's our annihilation and creation operators. And if I want to know what the number operator is in this state, and the number operator is just simply the operator Ni. Sometimes I put a hat on, sometimes I don't. But I'm just putting it on for now, just to make sure that people realize that it's an operator. Okay, so that's the number operator for the single particle quantum state labeled by I. Okay, so then you can say, well, all right. So what does that mean for this density matrix? So the next thing we're going to do is we're going to write down the density matrix. Use this definition in the density matrix. So we call it a matrix because it has an R prime. So we think of these things as being like the rows and columns of a matrix. Except this matrix, of course, is infinitely dimensional, but that's why we call this a matrix. Okay, so let's do that. So we're going to write down. We're going to simply take rho and R prime, and from that definition, from the definition over here for psi and psi dagger in terms of A and A dagger, we're going to plug that into the definition here for the single particle density matrix. So what we're going to do is just simply substitute these definitions, so substitute these into the definition. So let's write it out. It's a bit long, but we're going to write it out and then we're going to unpack it. So we get 1 over the partition function, the sum over states, our Boltzmann factor, eta minus beta n, and then I've got 2 powers of square root of v, so that means I'm going to get a factor 1 over v. Then I've got 2 k vectors, so I'll write them as k prime, and then I have n ak prime dagger, ak without a dagger acting on n, and then I have my Fourier transform e to the I k dot r minus k prime dotted with r prime. So what I want you to make sure you understand is that when I write down, oops, actually I'm going to do this over here. So when I write down this k here and here and here, this is what we call a dummy variable, right? It's summed over. So I can call it anything I like. So when I write down a product of two psi's, I have to make sure that I use a different dummy variable with a different variable name, otherwise I'll get them confused. So in one of the operators, I use k, and in the other operator, I use k prime, and they're both of those k's are summed over, and they're summed over right over here, as you can see. So I should have silenced my iPad, but too bad. Okay, so now we're going to evaluate this, and the way we're going to evaluate this quantity is we're going to look at what this matrix element does over here. So I claim the following, that if I compute n ak prime dagger ak acting on n, so I claim that because the momentum eigenstates are orthogonal, unless k and k prime are the same, then this thing is going to be 0. If they are the same, then this thing is just going to be the number operator. So basically, this thing is going to be the number operator nk acting on n, and then it's going to be 0 unless k is equal to k prime. So that means we have a Kronecker delta k of k prime, and this is because the momentum states are orthogonal. And so what that means is that when the AK acts on the n to the right, and when the AK prime acts on the n to the left, those will create two different states with different momenta, and so they'll be orthogonal. And so that's how we know that's the case. So then what that means is, so since this object over here is now just proportional to a delta function, that means that k and k prime in this exponential here are going to be the same. So what that means is that now we've beaten this thing down into the form rho of r and r prime is now 1 over v, and then the sum over k, because there's only one k now, the expectation value of the momentum or of the number operator in state k times e to the I k dot r minus r prime. Okay, so that's our final formula. Or at least our intermediate formula. So now let's ask what this value is. What is the value for ideal bosons? And we know there's going to be two different cases that we have to consider. One case that we have to consider is that we're above the Bose-Einstein condensation temperature, and one case is when we're below it. So I'm not going to calculate it in a strict way. I'm going to just explain to you what must happen to it, okay? Because I want you to understand how it works rather than just simply plug into a formula. And the reason I want to do this is because we can use a similar reasoning for an interacting system. So if we're above Tc, so we have to look at T greater than Tc and T less than Tc separately. Okay, so above Tc. So what's going to happen above Tc? Well, what we know is that above Tc, all the occupation numbers are basically just some number. They scale as 1, and they don't scale with the system size. So what we know is that if I take any arbitrary k state, then its occupation number is a quantity of order 1. And what I mean by that, by order 1, is that it stays a constant as I take the thermodynamic limit. So in other words, it doesn't scale with the number of particles in the system. And so what that means is if we just replace nk as some number, then what that means is that if we replace nk then what would happen is the formula here would be rho of r and r prime is something like 1 over v sum over k e to the I k dot r minus r prime times some number. So it's basically something like that. In other words, it's something like a delta function, because this is just the representation of a delta function. Okay, so that's what this quantity is. All right, now it may be slightly modified from that, but it's basically something that is certainly going to be peaked around r minus r prime. So now what we do is we take the limit as r minus r prime goes as far apart as possible, goes to infinity, and that says that rho of r and r prime in that limit is going to go to 0. So basically what I've told you is that if I'm above TC, every quantum state has some occupation number, which are more or less the same. They're just particular numbers, nothing special happens to them. And so that means that the rho of r and r prime is either going to be a delta function or maybe some slightly peaked function around r minus r prime. So it's either going to be this or a peaked function. And so when I take r minus r prime going to infinity, so the two points where I'm measuring are far apart, then what I'm going to get is that rho of r and r prime is equal to 0, and that is true for t greater than tc. So that's the first statement that we can make. So now what's happened below tc? So now what we know happens is that we actually have Bose-Einstein condensation. And so what that means is macroscopic occupation of the ground state. In principle, it could be a current carrying state as well, but we'll just say for the present argument, just the ground state. And when we say macroscopic occupation, remember what we mean by that. Implies that there is a non-zero fraction of particles in a single quantum state. And I've underlined the word fraction because that's the important point. The number of particles scales with the number of particles in the system. And so, oops, I want to go into here. And so the fact that it's a fraction rather than a fixed number is the most important point. So that means that if I were to write down what the expectation value of nk is, the number operator, so what we've just said is that is equal to n naught, the number of particles in the ground state, delta of k 0, and then plus some occupation of the excited states, and I'm going to write that down like this. So this part here, F tilde, this is meant to represent the occupation of excited states. And this thing is of order 1. And I say order 1 in the sense of the thermodynamic limit. And again, because it's like that, it will give us a 0 contribution. This part here, this part here is not of order 1. This part here is of order n, because we have macroscopic occupation. So there's a fixed fraction of particles that are in that state, and so it's order n because it is a fixed fraction. Maybe a small fraction, but what it means is that as I change the system size, change the number of particles at constant density, change the volume of the system, then the number of particles in the ground state scales accordingly. So what that means is that when I now calculate what is the contribution to rho of r and r prime, this thing is going to give 0 contribution to rho of r and r prime as r minus r prime goes to infinity, just as we had before. But now let's work out what is the contribution from the condensate. So if I plug this formula into my definition of rho and r prime, what you're going to see is let's go back to here. So now let's look at this formula here. So if I put nk is equal to k is equal to 0 in here, then what it's going to do is it's going to give you a contribution 1 over v sum over k delta of k0 times n naught times e to the I k dot r minus r prime. And what that contribution is, well, k is equal to 0, so this is then just, this thing then just becomes, when k is equal to 0, this thing is equal to unity, and so what we end up getting is just n naught over v. And so in the end, what I have then is rho of r and r prime is equal to n naught over v. It doesn't depend on r minus r prime. And so now if I take the limit as r minus r prime goes to infinity, and I've squeezed it in there rather small, hopefully you can read it, then that limit still gives me a value which is n naught over v, which is a number which is non-zero. And so this then is true when t is less than tc. So what I've got now is an order parameter which is 0 for t greater than tc and non-zero for t less than tc. And what do we call this thing off diagonal long range order. So let me say why we say that. So what I've got here is rho of r and r prime, the limit looks like this. So the first thing is that this is called, the fact that I'm taking this limit to infinity, that means that I'm looking at long range, because I'm taking 2 points which are far apart. The fact that R is not equal to R prime means that it's off diagonal. We think of this thing as a matrix, then R and R prime are different from each other, and so they're off the diagonal. And the fact that this thing is not zero means that I have order. And so that's why we say that this statement here is really a statement of off-diagonal long-range order. So if I have a classical system, I might have a similar kind of long-range order, but it would be for a correlation function. So let's just compare this with a classical system. That has, for example, a correlation function of some order parameter, such as magnetization. So then I might have G of R prime. That might be the thermal average of the magnetization at R, magnetization at R prime. So something like this. And I might say, well, in this particular case, I might have long range order. So if I look at the limit to R minus R prime of G of R and R prime, if that is non-zero, then that again tells me that I have long range order. We don't tend to think of this as a matrix because it's not like a density matrix as in quantum mechanics. So we just simply would call this long range order. And what does the 2-point correlation function mean? So what this really means is the probability of finding order at the point in space R, given that there is order at R prime. And that's the meaning of this correlation function. Okay, so that's long range order. So now we've got long range order classically, and we've got long range order quantum mechanically. So now let's generalize this a little bit more to arbitrary quantum states. So how do we do that? Well, let's suppose we had a condensation into a wave number, not k equals 0, but k is non-zero. So suppose we had a macroscopic occupation of a state with wave number q, which is non-zero. Then the way I would construct the off-diagonal long-range order would be like this. I would say take rho of R and R prime, and now what I'm going to do is I'm going to define this to be 1 over the volume. Now it's going to be the occupation number of the state Q, and then I'll have in here e to the I Q dot R minus R prime. So that would be the generalization, condensing into a state with Q, and then I would take the limit as r minus r prime goes to infinity, and that would be the generalization of off-diagonal long-range order in that case. Now, of course, I can then add a whole bunch of plane waves, and so now we can generalize further, add up many plane waves to get condensation into a state with spatial wave function which I'll write phi of r, like so. And so then my definition of long-range order would be this thing. It would be like that. So that's the idea of how you would generalize a Bose-Einstein condensation into this kind of order parameter. So far everything that I've told you is for bosons, to ideal bosons. And what we're going to now conjecture is this is a conjecture first made by Yang in 1962 or something like that. So what Yang suggested was that the same thing is true, that off-diagonal long-range order occurs even in an interacting bosons. And so that's the conjecture. And so we're going to assume that that is correct. And so what we're going to look at now is what are the consequences of this conjecture. So this is a section 2.4.3 off-diagonal long-range order and superfluidity. So what is our goal in this section? So our goal is to use the notion of off-diagonal long-range order to understand the existence of persistent currents. Oops, I made a typo here. And what do I mean by persistent currents? What I mean is essentially perpetual motion, that I set a system up with a current, and then I just let it go, and then that current will just keep on going forever. So we can think of this as a kind of quantum mechanical perpetual motion. Very long-lived currents in a particular geometry, and I'll show you exactly where that comes from. So that's our goal, and the way we're going to show this is we're going to consider what happens when we have macroscopic occupation of a single quantum state. So let's just suppose that this has all happened. So suppose we have macroscopic occupation of a state which I'm going to write down as phi of r. Let's write down that state as an amplitude and a phase. So there's an amplitude I of r, A of r, and then a phase, which I'll write as gamma of L. And for now, let us normalize. So we'll say that we're going to define a quantity rho naught to be the magnitude of a squared. And this is going to be something like a superfluid mean density. Now, I'm going to be cagey about what this really means, because later on we're going to talk about the difference between superfluid density and the number of particles in a condensate. And so I want you to bear that in mind, because what I'm saying here is something we're going to make a bit more precise later on. So right now, I just want to give you the general ideas for this. So now we've got this single, we've got the singly occupied state. So the Schrödinger equation for this state, we can write down. So that's I h bar d by dt of phi is so minus h bar squared over 2m del squared phi plus some potential phi like so. And if I work out the usual thing about the probability current, so if I work out d by dt of phi squared, then that is just minus the divergence of a current. And I can write that current as phi star, the momentum operator acting on phi, plus its complex conjugate, and then multiplied by 1 over 2m. So, and the momentum operator is just minus I h bar grad. So this is all something that you learned on your mother's knee. And so what that means is I can write down that the density of the state is given by some equation of continuity, and the supercurrent density is this thing which I've called JS, which is 1 over 2m phi star p phi plus the complex conjugate. Okay, so that's just simple quantum mechanics. So now let's write this in terms of the phase. So now we remember that phi is equal to a e to the I gamma. So if we just plug that in, then what you get is that J is equal to rho over m h bar, rho naught over m, h bar grad, what happened? Grad gamma. So in other words, that the current is actually proportional to the gradient of the phase of the wave function. So all we're doing is just plugged this formula straight into here, and we're going to write this. We're going to write this as rho s times vs. I've called this rho 0, and I'm going to really just call it rho s for now, even though I don't really think it is rho s, but never mind. So let's just put this like this. So we'll call this rho s vs, and why do we write it like that? Well, any current is just a density times a velocity. So therefore, so that's all this formula says. And so this says that the super fluid velocity Vs is just h bar over m times the gradient of the phase of the wave function. And why is this cool? Why is this cool? Well, remember that we're trying to understand superfluidity. So so this says that superflow is potential flow. What I mean by potential is that it is the gradient of some potential. And that potential is the phase of the wave function. So that's something that's really quite remarkable, that we have a connection between the phase of the wave function and the superfluid velocity. Now, the other important thing, or let's just say super important, is this. If I have V is grad gamma, then it means that if I take the curl of V, that's going to equal 0, because the curl of any gradient is identically 0. And so this is exactly the condition for superfluidity. And what we showed was that meant that it exerted no drag. It was the no drag formula. It didn't mean that the viscosity was 0. It just meant that the superfluid exerted no force. So essentially, what we've just learned from this exercise is that by condensing into a macroscopically occupied quantum state, with a well-defined phase for a macroscopic number of particles, we've derived the idea that you can have superflow. And so this is really fantastic. Okay, so we still have time. So what I'm going to do now is I'm going to talk about persistent currents. So the next thing we're going to discuss then is the implications of this for persistent currents. Okay, so the basic idea that I want to discuss now is that we consider a superflow in a geometry that is not simply connected. In other words, there is topology. So we're going to look at superflow in a non-simply connected topology. Okay, so it sounds ominous, but really all I mean by that is that we're going to consider the flow in an annulus. So here's my annulus, like so, and we're going to assume that this annulus is filled up with superfluid helium like that. Okay, so what is the idea? What we're going to do is we're going to track the wave function as we go around this annulus. So let's draw a curve in the middle of it. We'll draw that curve C, like so. Excuse me. And I'm going to look at it at different points. So I'm going to call this point here R1, this point over here, R2, this point over here, R3. And then what we're going to do is we're going to look at how the phase of the wave function varies as I go round this curve. So that curly C is meant to be this curve here. Okay, so let's draw. Let's consider what are the possibilities that we could have. So we're going to write down that phi of r is equal to some constant times e to the I gamma of r. So the only spatial variation is in the phase. Okay. So first of all, if we have a gamma of r is equal to a constant, then what's going to happen? Well, according to this formula over here, then what's going to happen is that the velocity is going to equal 0. So nothing interesting will happen. Okay, so now we want to look at case 2, where gamma of r is not a constant. So what might it look like? So to answer that, I'm going to draw the Argand's diagram, and we're going to look at what the wave function might look like. So this is the real part of phi. This is the imaginary part of phi. And I'm going to draw this for all of these positions. So this is going to be R1, this is going to be R2, and this is going to be R3. And now let's draw what gamma looks like. So over here, it might be like this. Over here, it might be like this. And over at R3, it might be something like that. So from this, we can measure gamma. So here's gamma, gamma, and gamma. Okay, so now what happens as we go around this loop in the annulus? So the question we now need to ask is what happens as we go around the loop? And I realize I'm 3 minutes over and I've got 1.5 minutes to go since I started talking. So I'm going to just finish this and then we'll quit for today. So the question is, what happens as we go around the curve C? So the answer is that as we go round here, starting from say R1 and go all the way round, what's going to happen is by the time we go round the curve and get back to R1, start at R1, go round past R2, past R3, and back to R1. What's got to happen here is that the wave function has to be single valued. And so what that means is, as we go around the curve in real space, what has to happen is that the gamma must have changed by a multiple of 2 pi. So what that means then is as I go round, that means that the implication is that each change in the gamma as I go round the curve corresponds to the quantization of the velocity. And why that is where we will begin next lecture. Okay, so I'm going to hit the stop button, and then next time we will pick up on velocity quantization.